We're here to celebrate the 168th birthday of Nikola Tesla. And remember, at the birthday parties that he held, you would get congratulations and appreciation from scientists and engineers all over the world. Who was Tesla? 1856 to 1943. The story really starts, though, on the pathway in the Vörösliget in Budapest, where Tesla, with a stick on the sand, lays out the concept of the rotating magnetic field. And that changes the whole 20th century. That's another story for another time. We'll briefly talk about, though, the rotating magnetic field. Here's a comment by Sir Arthur Fleming. Tesla conceived the idea of winding the Grammy magnetic ring not with one continuous coil like a toroid, but with two independently spaced coils 90 degrees out of phase. This was something new. Later on, 6 years later, in May 16th of 1888 at Columbia University, when Tesla gave his talk, he said, "I've demonstrated the complete analogy between the ring and a revolving magnet." You can see the ring on the left, and on the right is in fact the coordinate transformation that Tesla writes down and is in that lecture at Columbia. That little gadget that you're seeing there, this is from the internet. People on the internet have done some marvelous videos. This is called the trammel of Archimedes. However, it operates on the same principle that Tesla's using for the rotating magnetic field. Dr. Kapp, who was in the electrical engineering department at the University of London, wrote this: "Before Tesla, a magnetic field appeared to be firmly attached to the piece of metal in which it originated, moving when it moved and at rest when it rested. The notion that lines of magnetic flux could slip over the armature, that an invisible moving field could be produced by a stationary metal, that a magnetic field could rotate when it was produced by copper and iron that did not move, was alien. The invention of the wheel is somewhere in the distant past. Some caveman invented the wheel, but the invention of the wheel was perhaps rather obvious. But the invention of an invisible wheel made of nothing but a magnetic field was far from obvious, and that is what we owe to Nikola Tesla." 40, 60 years, 50 years later, after the lecture at Columbia, Leigh Page, who was chairman of the physics department at Yale University, wrote, "The rotating armatures of every generator and motor in this age of electricity are steadily proclaiming the truth of the relativity theory to all who have ears to hear." What did Tesla have to do with that? Well, the idea of rotating coordinates was something new, and it's going to change the whole history of physics. By 1939, the Oppenheimer shift paradox becomes apparent. It's a fabulous, remarkable paradox. Mach's principle. All these things are built into this notion of rotating coordinates. And by 1916, when you read the first paper on the general theory of relativity, Einstein has incorporated virtually the same transformation that Tesla has scribbled in the sand there in Budapest. What we've got here are, Einstein said, look, the laws of physics are invariant, form invariant. They don't change. Maxwell's equations are still Maxwell's equations when you're in the static frame or in the rotating frame. And what we have here are, in four-dimensional form, Faraday's law is on the top. We have the rotational transformation, and you get Faraday's law in the rotating frame, coordinate frame. But the amazing thing is, what appears is in the frame of the stator in the motor, you have a magnetic field. But in the rotating frame, you get an additional electric field. And not only that, now you got to realize that the curvature tensor is vanishing, is zero in the frame of the stator. Since it's a tensor, it must also be zero in the frame of the rotor. So we didn't change the curvature of space-time, but an amazing thing occurs to the geometry of the space. In the static frame, the ratio of the circumference to the diameter is pi, going all the way back to Pythagoras and the Greek geometers. However, when you take the ratio of the circumference to the diameter in the rotor frame, what you get is a number that's bigger than pi. Pi is not an absolute. The biggest machine that I can think of here on the planet is the Large Hadron Collider at CERN. And this is really a motor after you look at what's going on here, with a rotational motor speed of 666,000 revolutions per minute, which is about 70,000 radians per second for the angular velocity. There are bigger rotating fields, and of course what comes to mind is the magnetic field in the Jovian dynamo system. You can see this little cartoon is from the European Space Agency, and you can see the plasma torus that's surrounding Jupiter. And if you look real close, you'll see the planet Io there. And as the conductivity of Io is big enough so that as it moves through that plasma torus, it creates a potential difference from pole to pole that creates that vertical flux ring that transmits huge radio signals, principally in the 20 megahertz region, that you can hear on conventional shortwave radios. Even bigger rotating fields in the cosmic. When I was a grad student back in the 60s, one of the big things was this quasars had just come along, but nobody had an explanation for this jet. If you look in the figure 1 here, M87 is a giant elliptical galaxy with a rotating black hole in it. At least that's what we have for a description today. The diameter of M87 is about 100,000 light years. It's about 35 million light years away from us. And it has this blue jet that you can see issuing off going off to the upper right. That's about 3,000 light years away. Back in the 60s, nobody knew what the explanation was. Since then, people have hypothesized that what's going on is a huge rotating black hole in the nucleus of the galaxy that has this spinning magnetic field that's producing a modification of the geometry, local geometry. Back then, people had just learned about the Kerr metric, and since then they've been able to add electric charge to it. So we have the Kerr-Newman metric. And the geometry of space-time there is modifying the toroidal magnetic field around the black hole that ejects these huge jet of material. And the radio power output is about 10 to the 35th watts from this thing. It's like converting 10 to the 35th watts is 10 to the 35th joules per second of energy that's being blasted away here. All right, look, we said all that to say this, and here's a quote from Tesla in 1929. "My induction motor may be discarded and forgotten in the continuous evolution of the arts, but my rotating field, with its marvelous phenomena and manifestations of force, will live as long as science itself." Now, Tesla back then gave us the induction motor, rotating magnetic field. But what we're going to show here in the next few minutes is he also came up with a rotating electric field that makes a wireless transmission of power possible. It puts it on a sound technical base, and that's what we're after. Dr. Krauss, who was the head of the radio observatory at Ohio State when I was a grad student, said that the 20th century was the electromagnetic century. Every pinpoint of light that you see in this picture, taken by NASA back about 20 years ago, has been processed through the power distribution system invented by Nikola Tesla, every point. All right. Now, there's a lot of the Earth that's still dark. And what we want to see is that instead of using wires for polyphase power distribution, we can do it wirelessly. Dr. Krauss went on and said something even more profound. And he said, look, the 20th century was the electromagnetic century, but the greatest discoveries are yet to be made. Richard Feynman, Nobel laureate back in the early 60s, wrote, it's in volume 2 of his lectures that he gave to the freshmen at Caltech, power networks of the future may have little resemblance to those of today. He could foresee where things were going. And what we're interested in, all of that was a preface to this. We want to talk about Tesla's 1899 Prospect Lake demonstration. One of the things that struck me over the years was that we know so much electromagnetics. Here's a simple picture. This was published in June of 1900 in Tesla's article. And the caption on it reads that this is an experiment to illustrate the transmission of electrical energy through the Earth. Now, you got to realize he's saying through the Earth. This is 1899. I think it would be appropriate to say by means of the Earth, because we're going to see that the Earth is functioning as a waveguide. Okay, there's some physics here. Without wire, he says the lower end is connected to the ground. All right. In 1916, when he's explaining this to his lawyer in a legal briefing, he says that little lamp is nothing spectacular, but this is a great experiment marking an epoch in the art. And what struck me is, all right, look, we can see this. It is a coil and a light bulb lit up. He's about 1 kilometer away from where the transmitter is. We know what the properties of his transmitter are. And in fact, he tells us he's running about 10 kilowatts here. And he gives us the frequency and all the particulars. Why hasn't somebody done the calculation to see he's claiming he's getting 10 watts here in this light bulb? Where's the calculation? We ought to be able to explain this. And that's where we're going with this. Now, Ken and I were in Belgrade in 1983 and again in 1986. Ken has made several other trips there to the museum. And one of the most inspiring people that we met was, and we'd like to dedicate this little talk to the memory of Professor Alexander Morenchich. In 2006, Morenchich wrote a book chapter, and he said Tesla was the first to generate a ground-guided wave, which soon became the only one used in the early development of radio wave transmission. When we were there in 1983, we were of the mind that Tesla's experiments had something to do with the Schumann resonances. And at the time, Dr. Morenchich indicated he thought it had something to do with surface waves, which are a different phenomenon. And it took us about 10 years to finally come around and agree with Dr. Morenchich. So in the early 90s, we started pursuing the fact that Tesla's wireless transmission was a guided wave, a surface-guided wave. At the time, the distinction for us between the Norton ground wave and the Zenith surface wave was not clear. Of course, that's changed. I also need to mention the impact of Dr. Jim Waite, and I'm permitted to call him Jim because he told me I'd call him Dr. Waite. He says, Jim, don't call me Dr. Waite, call me Jim. So, okay, Dr. Jim Waite wrote this in 1998. Now, he died in October of 1998. So the full story of the incorrectness of the Sommerfeld sign error, he believed that Sommerfeld had made a sign error, and that story hadn't been untangled yet when he passed away. But he wrote this in a review article. Early conjectures, such as by the prophetic Nikola Tesla, were that the signal was guided in some fashion by the air-earth boundary. Okay, so far so good. The pervading idea was that the presence of the Earth was a key factor. This was the beginning of the subject that we now call ground wave propagation. And Dr. Wade has done just tremendous number of papers in his career on ground wave propagation. Kenny and I, as we read through, any professional, as they read through the Tesla literature, comes across one puzzling assertion made by Tesla after another. And we've got a list here of 15. I think there's about a dozen more that have bothered us over the years. This stuff about ball lightning and the planetary signals and capacitance increasing as a ball goes up. And Tesla said he discovered a transformer, a way to take DC to DC and have it raised on a transformer and have it increase. Now, this is DC on a transformer, but have the old output voltage increase by the turns ratio. And it's like, none of these things make any sense. And so these were mysteries to us. But one by one, as we've gone through, when our belief has been, if Tesla said he saw something, then he saw something. What was it? And as we've gone through all of these mysteries, one by one, I think what we've uncovered has been, yes, if you do what Tesla said he did, you will see what Tesla said he saw. We've talked about the first 7 of them, many times, many places. I've written many papers, but what we want to zero in on today are mysteries 8 through 12 here. The mystery of the longitudinal non-Hertzian wave. Tesla was adamant about that propagating fields are non-Hertzian, yes, and that they were longitudinal, not TEM. Well, it turns out he's right. They're not TEM. But the mystery is, well, why did he say they're longitudinal? Because Shelkonoff has gone through proof that all electromagnetic waves are transverse. They can be transverse magnetic, that is TM. They can be TE, they can be TEM, or they can be a mixture of the above, a hybrid mixture. And he discussed all that back in 1943. So the question is, well, what is Tesla talking about? Then there's the crucial Seneca-like justification of the sign error and the impact that it had on the whole of 20th century electromagnetics, and why we think that electromagnetic theory has been flawed since 1936. And the correction was actually made in 2004. And when you go through and look at what was corrected and what the impact is, I think you begin to understand how Tesla was doing wireless power transmission. There was this mystery that we just showed you of the little light bulb being lit up about a kilometer away from the transmitter. And then there's this mystery of O'Neill's anecdote where he talked with Tesla, and he reports that Tesla lit up a bank of 250-watt light bulbs 26 miles away. Is that possible? Well, I think you're going to see something that you may find interesting here before we're through. And finally, the mystery of the global resonances. Global resonances date back to J.J. Thomson and Fitzgerald, as well as Tesla, all in about 1893. But there's a new twist on all of this that I think is really important. Okay, so here we go. While Tesla was inventing the AC motor and developing it, now remember the lecture at Columbia was in May of 1888. Right at that same time, Hertz in Germany is developing the notion of electromagnetic radiation. The top quote here is from Hertz in Hertz's paper. Many a man has thrown himself with zeal into the study of Maxwell. Of course, he's writing this in 1891. I have rather been guided by Helmholtz. Now, Helmholtz was another guy that believed that electromagnetic waves were longitudinal waves. So don't hold that against Tesla. But look at the Hertz oscillator. If you look at it real close, you'll find out that it is, in fact, a variation of the RLC circuit studied by Lord Kelvin in 1853, I think it is, where he publishes, the Proceedings of the Royal Society. He was the one that formulated conservation of energy for electrical circuits. He charges up a Leyden jar and discharges it through an inductor. Wrote the second order differential equation and got underdamped, overdamped, and critically damped circuits, the kind that EE sophomores have been studying ever since. What Hertz did was he needed an oscillator, so he took the capacitor plates and opened them up, and you can see the two plates here forming a dipole. The inductance is the inductance of the wires, and he brings in high voltage from a buzzer, essentially. And as the voltage reaches a peak that's large enough to spark across the gap, the plasma conducts and the two capacitors discharge. And when they do, you get an oscillating current between the two that sets up a standing wave on the structure, and more or less, and radiates a damped oscillation. All right, well, that's the idea behind the Hertz oscillator. Marconi essentially took that Hertz oscillator, turned it up as a monopole, eliminated the one side, essentially uses image theory, and has a monopole oscillator that works at much lower frequencies. Hertz's experiments were in the 50 to 150 megahertz region. Marconi's are going to end up down in the hundreds of kilohertz region. Well, let's see. Tesla wrote that Hertz's results caused a thrill as had scarcely ever been experienced before. This is from Wikipedia, and is you can see the energy coming off from this and radiating out into space. Tesla's comment. Now, I realize Tesla's a power engineer, and he looks at this, and speaking as a power engineer, he says, look, the radiation goes out in the form of rays. It's unrecoverable. As a power engineer, I realize 1893, they've got the Niagara Falls power plant plans, and they're getting ready to go. And I think it's finally turned on in 1896. But he says, look, radiation goes out in the form of rays. It's unrecoverable. It's hopelessly lost. All goes out into space, never to return. In 1892, Tesla gave a lecture at the Institution for Electrical Engineers in London. And he was persuaded by Sir James Dewar to hold over and that was on a Tuesday night, and Dewar persuaded him to hold over and speak to the Royal Institution on Thursday night. And he eventually, by August, that was in February, by August, he shows up on Hertz's doorstep. Hertz was then at Bonn at that time, and he confers with Hertz, and turned out Hertz wasn't too impressed with Tesla, and Tesla wasn't too impressed with Hertz. But at that point in time, Tesla was already generating RF power 10 to the fifth times what Hertz had. Now, Tesla made this puzzling assertion that has been a source of embarrassment to professional people in electromagnetics. He said, look, now realize what Tesla's saying. I consider this extremely important. All right, so that means this is important. Light cannot be anything else but a longitudinal disturbance. Red flags go up all over the place. That can't be. All right, but he said, light cannot be anything else but a longitudinal disturbance. Wireless waves are of the same character as light waves, only they're not transversal, but longitudinal. Now, why would he say that? What did he see that made him think that? All right, and again, our experience has been, if you do what Tesla said he did, you will see what Tesla said he saw. All right. To understand what's going on here, you've got to go back. This is 1915. This was a IRE, Institute of Radio Engineers, now IEEE, banquet being held at Luchau's famous German restaurant. What is it? It was there in New York City. Everybody that is famous in the world passes through the doors of Luchau's. It's a German restaurant. On the left, you see George G.W. Pierce from Harvard University. Next to him is Carl Ferdinand Braun. Braun gave us the oscilloscope, and he also is the father of phased arrays. Now, that's important. Next to him is John Stone Stone, who was the president of the IRE that year. On his right is Jonathan Zenneck. Now, Braun received the Nobel Prize, shared it with Marconi in 1909. And Braun and Zenneck were in New York, along with Nikola Tesla, as consultants in a case that was being tried against Marconi. All right, next over, of course, from Zenneck is Lee DeForest, and then here's Nikola Tesla, and next to Tesla is his assistant at Colorado Springs in 1899, and that was Fritz Lowenstein, who also played a major role in the invention of radar, and a whole bunch of other famous people. Now, Zenneck and Tesla shared a lot in common. Zenneck, by the way, was the first fellow of the Institute of Radio Engineers. They had made him a fellow at this point in time in 1915 when he was in New York. And by the way, World War I had just broken out. Zenneck was put under house arrest because we were fighting the Germans at the time. And they arrested him, put him on Ellis Island, and then later transferred him to Fort Oglethorpe in Georgia. But he and Tesla spent a good bit of time together. Now, there's something interesting going on here. And years later, in 1931, Zenneck writes to Tesla, "The hours I was permitted to spend with you, I will count as the happiest moments of my life." And it's no wonder. Realize that's in 1931. Zenneck, in 1907, realized in December of 1901, Marconi had transmitted across the North Atlantic. And people said that's impossible because using electromagnetic radiation, because the rays travel in straight lines, and essentially because of the bulge of the Earth, you've got a 100-mile-high wall of salt water, and there's no way that Hertzian waves are going to pass through that. Zenneck was looking for an explanation at the time. Today we know it's because of sky waves in the ionosphere, but in 1907 that wasn't clear. And in 1907, Zenneck came up with an exact solution of Maxwell's equations for a surface wave. What Zenneck did in 1907 was he found, and I said an exact solution, that's important. And I remember the first time I learned about Zenneck waves was in 1967 in a grad course. No, it was summer of 1966 in a grad course on antennas at Ohio State. And I remember the professor saying, well, there's solutions of Maxwell's equations that just aren't physical. And of course, that was a position that was held by the folks at Bell Labs from back in the 30s. And I thought was, how could you have an exact solution of Maxwell's equations and it not be physical? Anyway, here's the way that Zenneck got his solution. Now, he does it in rectangular coordinates, and we've kind of presented it here because it'll be helpful for us to light up that little light bulb in cylindrical coordinates. And essentially what Zenneck did was he assumed a transverse magnetic wave. He doesn't tell us what the source is, and that's been a major issue over the years. But he gets a transfer. So here's H sub phi, which is the TM part of a wave. He essentially assumes this form. It's exponentially decaying up from the surface of the Earth, and it expands as a radial ripple. We call them Hankel functions, which are superpositions of Bessel functions of the first and second kind. That's solution. They're the eigenfunction solutions of the wave equation. Okay. Giving that, and if you write Ampere's law in cylindrical coordinates, so you see there's the curl of H has got these two components, it's got a rho component and a Z component. You equate that to the right-hand side of Ampere's law, which is sigma plus j omega epsilon. That's an impedance or an admittance times the E field, and the E field has a rho component and a Z component. So it's real easy to solve for the rho, E sub rho and E sub Z. And here they are, two more expressions, Hankel functions of the first kind and of the zero, and they're radially propagating. That's the H upper 2, and they exponentially decay away from the surface. This isn't a radiation field. This is a guided wave, all right? And it's the kind of guided wave you can have over the surface of the Earth. And it's very similar to the kind of guided wave you could have if you had a radial transmission line. The only difference would be how it decays exponentially in the vertical direction. The ABB is the constant. It's the arbitrary complex constant. And that can be found from the boundary conditions. And usually what you can do is take the limit as Z goes to 0, and as you collapse in on rho asymptotically, you got to match that to any currents back at the source, and you can determine what the constant is. Well, let's see. We've got the constant down here. All of these parameters here, the K's are the propagation wave numbers, and the U is a propagation wave number in the Z direction, and the gamma is the one in the radial direction. All right, bunch of arithmetic here, but it all has deep physical meaning. Now, the critical piece in all of this is this complex index of refraction. And notice that the index of refraction is frequency dependent. If you go to real high frequencies, the omega, the 1 over omega term here can swamp out the second term in the index up in the optical region. Usually, it's just the index of refraction is just a function of the permittivity of the medium. But as we get down to these low frequencies, that second term can be a really important term, especially if our medium is dirt, the soil of the earth. All right, so we're going to plot E sub Z as a function of range that we can measure in kilometers at different frequencies. At 10 megahertz, notice the knee in the curve occurs out here, at about 1 kilometer or so. I think that's kilometers, yeah. If I go to 1 megahertz, notice the knee in the curve has moved out further. Now the knee in the curve is a little out beyond 10 kilometers, 20 kilometers, 30 kilometers. If I drop down to 100 kilohertz, which is near where Tesla was at Colorado Springs, again, this is the Zenek wave we're plotting. Notice the knee in the curve has moved thousands of kilometers, okay? And if I go down to 10 kilohertz, by the way, this is assuming the whole Earth is made out of dirt, okay? Notice the knee in the curve has gone beyond the antipode. And if we realize, most of the Earth is saltwater, it's gone even further. All right. So at real high frequencies, we wouldn't see this, but at real low frequencies, this thing is global. Okay, so here we plotted them all so you can see the whole family of curves at one time. So this is the electric field strength in millivolts per meter versus the range in kilometers. At 10 megahertz, 1 megahertz, 100 kilohertz where Tesla was, and 10 kilohertz where he claims at Colorado Springs he went as low as 10 kilohertz. Okay. What is a Zenek wave? A Zenek wave is a wave incident onto a medium that has no reflections. So the wave just is leaking into the lower medium as it propagates along. A Zenek wave is an inhomogeneous plane wave incident onto a flat surface at the complex Brewster angle. Now this was known to Zenek. So the critical thing here is, how am I going to get a wave that is incident at a complex Brewster angle. How do you make a complex angle of incidence? You can say, well, I'll just go at the ordinary Brewster angle. And no, that won't give it to you because your phase isn't right. It'll give you a minimum in the reflection coefficient, but it won't give you a zero. In order to get a null, you've got to make the incident wave be at the complex Brewster angle. How do you do that? Well, that was a mystery to us, and realize here's the index refraction. It's a complex number. For a Zenek wave, you want this angle of incidence measured with respect to the normal to be a complex. It's the angle whose tangent is equal to the index refraction. And if you do that, then the standard Fresnel reflection coefficient, the numerator will be 0. So you'll have no reflections. But the question is, how do I make that complex angle of incidence? And the answer is, well, it's not so bad. This is a key point. Geometrically, if you look at the little components of the incident E-field vector, you'll see that the ratio of EZ to E rho is the tangent of the angle of incidence. And that tangent of the angle of incidence is complex. So the idea is a simple one. And I think if I'm not mistaken, we patented that a number of years ago. But the idea was to control the phase of the E sub rho and the E sub Z and get the magnitude just right. And here's the logical conclusion. To make the reflection coefficient be 0, you've got to have the incidence at the complex. Geometrically, it's this. So what does it mean? Adjust E sub Z to make the EZ-E rho ratio equal to the index of refraction. And what have you got? What do you get for that? You get a surface wave that's excited with no radiation field. That means these are non-Hertzian waves. Well, what are they? We've seen them before. They're guided waves. We're looking at a guided wave solution to the wave equation. Now, you've done that in waveguides and things like that. We've got a waveguide here, only it's only got the one side, just the surface of the Earth. But the propagation loss at these low frequencies is extremely low. We'll plot that a little bit later, and you'll find out that you can get to the antipode and back with less than 3 dB if you're below 20 kilohertz, which incidentally is exactly what Tesla said in his 1905 patent on wireless power transmission. So here's Zenek's solution. It's got H phi, an EZ, and an E rho. And notice that in Zenek's solution, if you take his fields and take the ratio, his solution was already at the complex Brewster angle. All right, well, why don't I just build an antenna then? And, well, any antenna won't work. You've got to make one that has the EZ to E rho ratio match the index refraction. Then what you get for your troubles is a Zenek wave. Notice that if you've got the EZ to E rho, they're out of phase. If they're out of phase, what that means is the resultant E vector is going to rotate around as an ellipse, and you've got an elliptical polarization. Now, not only that, but realize now what Tesla was saying about longitudinal waves. This isn't technically a longitudinal electromagnetic wave. It is a transverse magnetic wave with a longitudinal component. Now, Tesla knew he had E sub rho components. He knew it wasn't a TEM wave. All right, now, look. If you had an ordinary two-wire transmission like power engineers use, the voltages and currents fall off exponentially with distance. You have a knee in the curve, so you have this blue-shaped curve for ordinary transmission lines. If you had a radial transmission line, like two plates connected by a signal generator at the center, the radial transmission line would have this red-shaped curve, which is, it's a variation from just, I'm going to say, one-dimensional transmission line to a two-dimensional transmission line. But notice the behavior on this is an e to the minus alpha r over the square root of r. Okay. But if I had radiation, the radiation fields fall off as 1 over r, all right, which is this guy. And the vertical axis here is in dB. So you can see already we've got 20, 40, 60 dB worth of improvement or less loss by going to the surface wave transmission line, if you can do it. And the critical thing is, can we excite the Zenek pole? And you'll see what I'm talking about in just a minute. Now, that was 1907. In 1909, Arnold Sommerfeld at Munich, and Sommerfeld wanted to get the solution for an incremental dipole. He wanted in the presence of lossy media. By the way, Hertz's solution was in empty space. Zenek's solution he adds a whole new dimension to this, was the first solution for fields in the presence of a lossy medium. Okay, propagating waves in the lossy medium. He didn't tell us what the antenna was, but he got the solution, exact solution. Then comes Sommerfeld in 1909, who wants the solution for an incremental dipole, like say the Hertzian dipole, in the presence of a lossy medium, and he does it down on the ground. Later on, in 1926, he'll raise it up. But in 1916, when Tesla is explaining to his lawyer, to his attorney, in preparation for that suit against Marconi, Tesla, at that point in time, he'd already talked with Zenek. He was aware of the solution published by Sommerfeld. Sommerfeld's solution includes a Zenek wave in the 1909 solution. And Tesla says to his lawyer, note, for instance, the mathematical treatise of Sommerfeld, he's referring to the 1909 paper, who shows that my theory is correct, that I was right in my explanations of the phenomena, and that the profession was completely misled. Now, I think those last words, completely misled, are going to reflect what's going on between 1936 and 2004. All right, well, look, the top line here is a simplification of Sommerfeld's solution. It can be broken down when you write the integral solution. It's one of the most complicated integrals, complicated solutions of electromagnetics known to man. It's usually not presented until you get to one of the upper level graduate E&M courses at most universities. But it has several components here. And the first we kind of recognize as waves. And the way people explain it is from the transmitter to the receiver. The first term represents a direct wave. The second term represents a reflected wave, which can be considered as something coming from the ground reflected image. But there's this third piece that shows up in the solution of the wave equation that is a complex integral. Now, dW in this W is a complex wave number. And that accounts for this ground wave propagation. Notice that there is a pole, that is a place where the expression in the integrand blows up. There's a pole when this denominator term is zero. Now, double E's are really excited about poles and zeros because they tell you about the transmission of linear systems and so forth. That pole is what has to be excited. If it's not excited, you won't get a Zenek wave. All right. Now, I'd like to refer you to, there's so many books written on this stuff, but I'd like to refer you to Felsen and Markowitz's big old book. It's tough going, it's hard to read, but there's lots of good stuff in there. And they perform the integration and carry it out, and they get three terms again. The first term is the radiation field. That's what everybody gets. And that's what usually most people are after with building antennas. You want radiation. The second term is a surface wave term. If you go, P is what's called Sommerfeld's numerical distance. It's really the scaled distance R, scaled with respect to the complex index refraction, the magnitude squared. So this term varies essentially as 1 over the square root of R. All right. And then the third term is the asymptotic contribution. Now, here's what's of interest, and here's the part where people stumble. And I think Felsen and Markovits have it right. The third term is an asymptotic contribution. It nullifies the surface wave term. That is to say, it cancels it out as you're going farther out. When you go far out, what happens is you don't see the surface wave term. Why? Except over a restricted range of P, and that is out to the knee in the curve. Okay, now, look, the other thing about this that most people don't see is that you don't get this Zenek wave term if you don't excite the pole. All right. Here's the same thing again. This is the famous Sommerfeld half-space problem. When you look at the complex integral here, lambda is not wavelength. Lambda is the complex wave number in the radial direction. And you plot the poles there's a bunch of things you're going to see that happen. The wave number k is quadratic. That means it's multiple valued. And we call those branch points. And there are two k's that show up, one for the air and one for the medium. And they're quadratic. So what happens, you end up with four Riemann sheets to worry about. There's also the place where the pole is. And by the way, the poles in ordinary waveguides show up along this region. So, microwave engineers will recognize that part. Now, the interesting thing about this is over in wave number space, where the units are radians per meter. Double E's are used to time domain and frequency domain. Time domain in seconds and frequency domain measured in cycles per second or hertz, okay, or radians per second. Here we've got radians per meter and meters. So there's a Fourier relationship between the two, and you can see what the presence of the pole does. The presence of the pole gives us this extra little hump in here. The wave equation is a partial differential operator. The inverse operation, that is the solution, involves contour integration over a large circular path on the complex wave number plane, deformed to enclose singularities. And the singularities are the double-valued branch points, branch cuts, that is the Riemann sheets achieving single-valued integrands, and poles that are due to the boundary interfaces. If captured, and that's critical, if captured, the poles give residues that deliver discrete eigenvalues or guided wave modes. Saddle point integration asymptotically contributes a far zone field with a continuum spectrum of eigenvalues that nullifies the pole residue waveguide mode if k rho is much, much greater than 1. The pole-induced discrete spectrum is actually a guided wave, and the continuum spectrum gives Norton's radiation field. What Tesla demonstrated was a waveguide probe feeding power into a TM surface-guided mode. In the 20th century, everyone else accepted Norton's mythical sign error, justified by Burroughs' crucial Seneca-like experiment, and pursued antenna radiation. And here again is the comment from Felsen and Markovits. The wave character of the propagation depends quite strongly on the numerical distance, that is, how far out you go. Hermann Weyl came up with a solution in 1919, realized he's doing that about the same time that his first unified field theory, he comes up with the unified field theory before Einstein. His first unified field theory is he's trying to unify gravitation and electromagnetism. And on the side, he repeats the Sommerfeld 1909 solution, but he doesn't get the Zenek solution in here. Why didn't he get it? Well, it's because he was using this saddle point integration technique. And it doesn't show up because the saddle point integration technique only works out beyond where k rho is very, very large. All right, now look. The dashed line is the unattenuated field. It's what Hertz got, and really what Max Abraham got in 1901 when he does the Hertz solution over a conducting ground plane. So there's the radiation field. Zenik's solution is there's a dash line that comes in, and the knee in the curve takes it out of contention once you get out here beyond a certain range measured in terms of the numerical distance. The black line is Sommerfeld's solution. When people were measuring the fields from all of that, look, this problem was a really critical problem. Let's see, the grand old man of radio, Balthasar van der Pol, made the comment in the 30s that, hey, the economic impact of what's going on here affected every nation on the planet. I mean, this was a really big problem back in the 20s and 30s. The head of the engineer at the FCC by the name of Kenneth Norton was really important to laying out AM radio stations, the radio wave propagation problem. And he sat down and he said, we're not seeing this. There's something wrong with Sommerfeld's solution. And he goes through and he determines that Sommerfeld had made a sign error. Now, we're talking 1935. And that error isn't corrected until 2004. So almost 70 years go by where electromagnetics is taught, I'm going to say incorrectly. But here's Norton's solution, okay? And you can see that there's no, what Norton was able to do by throwing in this corrected or modified sign correction is eliminate the surface wave because it wasn't observed. In 1955, Sergei Shalkinov and Alfredo Banos got into a debate at an IEEE meeting. I think it was held in San Diego. But Banos comes up with, I think, the correct explanation. He says, look, at some intermediate range, the residue. Now, the residue is where what you evaluate at where the pole occurs, or the surface wave term, has a 1 over the square root of r dependence, and hence is the dominant part of the solution. However, for large R, the branch cut integrals. Branch cuts, I showed you where on the previous slide where the poles were, where the Zenik pole was, and where the branch points were. But in order to perform the integration, to keep the integrand as a single valued, you have to introduce, it's a Cauchy-Riemann integral. You have to introduce the branch cuts. And the branch cuts evaluation integral gives you the radiation field, whereas the pole gives you the Zenik surface wave component. Okay. However, for large R, the branch cut integrals asymptotically cancel out the residue term. Okay, so here's the formal mathematics. In free space, the eigenfunctions of the wave equation possess a continuous spectrum of eigenvalues. Those are the Hertzian waves. And the eigenvalues are going to be the values of the K rho. In bounded waveguides, the wave equation plus the boundary condition gives a discrete spectrum of eigenvalues. And those are the TE and TM waves modes that microwave engineers are so familiar with. In the present, here comes in general, in the presence of a lossy boundary, here's the Earth, the grassy field out there. The wave equation plus the boundary condition gives a continuous spectrum, the Hertz waves, plus a discrete spectrum of eigenvalues of the Zenik modes, if you excite them. All right. So I'm going to call it a Tesla interpretation of what's going on. And the issue is going to be, can we build one of these and make it happen? And I think that's where we're going. The yellow words up here are what Tesla actually said. He said this: the difference is the way I apply it. The radio boys want to apply my system one way, and this is how we interpret that, i.e., they want to excite Sommerfeld's branch cut integrals, resulting in Hertz waves, that is, in radiation fields. And he says, I want to apply it another way. What's the interpretation there? He wants to excite the Sommerfeld pole, which is a TM surface-guided wave mode. All right. He says, I'm not producing radiation in my system. He makes it, look, radiation resistance of a monopole, vertical monopole is proportional to h over lambda squared. He makes h over lambda real small so that h over lambda squared is even smaller so that he has effectively zero radiation resistance. I'm not producing radiation in my system. The energy flows through, that is, we interpret it to mean is guided by the surface layers of the Earth, as shown by Sommerfeld in 1909. He agrees on this theory. Now, this is what Tesla's saying in 1916. All right, in summary, the continuous part of the eigenvalue spectrum corresponding to the branch-cut integrals produces space waves, Hertzian waves, radiation. The discrete spectra and corresponding residue sum arising from the enclosed poles results in traveling waves that are exponentially damped in the direction transverse to the propagation. These surface waves are transmission line modes. That is, they're non-Hertzian waves. Aha! Now, notice this background is in purple here. This is important. If you didn't get anything else out of all that I said, listen to this. It is this surface wave and his spectacular apparatus, as you see in all the pictures, that completely distinguishes Tesla from all the other early pioneers of radio, even to this day. All right. Okay, that's been a lot of moon talk. We want to see the goods. Tesla's friend Mark Twain said it this way: war talk by men who've been to war is always interesting. That's where we want to go. We want to do some war talk. But moon talk by poets who haven't been to the moon, not so much. Well, we just did some moon talk. Franklin said this. He went through a lot of electrostatic stuff, but people don't realize what a significant Benjamin Franklin was, scientist to the world. He's the guy that gave us the plus and minus on electrical charges and currents. He's also the guy that gave us the notion of conservation of charge. Now that shows up 100 years later in Maxwell's equation of continuity, where Maxwell has to add the displacement term, and all of a sudden we've got wave equations and I'm going to say 20th century electromagnetics. We owe that seed notion back to Franklin. Franklin's comment was, let the experiment be made. Okay. Franklin did his experiment. You can see him holding up the knuckle there and getting the electrical discharge from the string, the kite string, in June 10th of 1752.